Hello, my name is Leila Kafari, and today I'm here on behalf of our research group here at CU Boulder under the supervision of Jet Brown. And today I'm going to talk about the use of automatic differentiation in solid mechanics software packages. So let's see when and how derivatives show up in solid mechanics problems. So usually a material scientist would want to think at the level of free energy functional. Here we are looking at Helmholtz free energy, which is a function of strain tensor E, and also a couple of constants like lambda and mu, which represent the material property. In real-world problems, we are dealing with nonlinear problems. And for any nonlinear problem, we need a nonlinear solver. This is a schematic of nonlinear solver. Usually, we have a initial guess. And so in this case, for forming the residual, we would want to take the derivative of the free energy with respect to E. And get S, which is the stress. And then by taking the second derivative of psi, or the free energy with respect to E, we can get delta S, which will help us to form the Jacobian. So the first step, taking the derivative of the free energy with respect to E, is usually not very challenging. But the second step can be very error-prone and time-consuming, so using AD could help us to develop our solver. And we could also avoid dealing with all these pieces and just take the derivative of the residual and have the Jacobian and avoid dealing with the debugging and all the problems with forming the Jacobian. In inverse problems, on the other hand, for example, people would like to calibrate the those Lamy parameters or the material property parameters, or they would even want to work with a more general form of free energy. So if they want to use a neural network, in common machine learning packages, what we usually have is that these inner layers are usually treated as black boxes, and we don't really have access to those inner layers. However, in solid mechanics applications, our input is the free energy, which is its energy. It's not interpretable or measurable. It is the derivative of psi or free energy, which is interpretable, and which will help us to debug our code, develop, and verify our code. So it would be helpful to have access to these inner layers. The first derivative of our input would be the stress, which is an interpretable object. And as we saw in the previous slide, the second derivative would be useful for solving our nonlinear problem. So we are interested in investigating these inner layers within a context, and we are looking for tools, AD tools that would provide this capability. Abacus is a broadly used software package in solid mechanics. It's fully automated, and it uses finite element method. On the left side of the slide, you see this is a user subroutine for introducing new material. And as you can see here, there are the user needs to provide the free energy, which is U here, and also the first, second, and third derivatives of the strain energy. And so as you can see here, this is a very complex interface, and taking these derivatives is error-prone and time-consuming. And also, the interface is such that it can introduce instability, especially for small deformations. So F is the deformation gradient, and the derivatives that Abacus requires are the derivatives with respect to somehow the deformation gradient. So if we have compression in a material, we would need to subtract, and if the deformation is very small, we would need to subtract a very small value from 1, and that's when we will have loss of significance. And that will introduce instability to our model. And since the interface is set up in that way, it's really difficult to get rid of that instability. And as software engineer, we know that the moment we set up a design, it's really difficult to change the interface along the way, because people will develop their models and codes with that interface. So that's why we are interested in AD tools that could help us to develop a more generic interface, basically having one input, a scalar function, and having the interface taking care of all the derivatives. For the experiments for this talk, we have used RATL. RATL is a new solid mechanics software package. It provides linear elasticity, large deformation, elasticity, multi-material. As you can see here, like these different colors represent the different material objects, static, quasi-static, and dynamic models, and also initial and current configuration. We will talk about this very soon in more details. So RATL is built upon a couple of software packages, one of which is libseed. So libseed is a purely algebraic high-order finite element method. And a cool thing about libseed is that the material scientists would need to develop the physics of the problem in one C code, and they wouldn't need to worry about the rest of the FEM implementation. It also supports various CPU and GPU backends, and we can run the code by choose the backend in runtime with a command line option. It supports matrix assembly and matrix tree, and the operator abstraction in libseed is such that so as you can see, I'm not going to go to the details of these objects, but for developing a new material, the user would only need to take care of the actually write the continuum mechanics of the problem at this level, and not worry about the rest of the implementation. And also, it provides the user to store data at the quadrature point and use the data later on, for example, in the Jacobian evaluation. Also, I should mention that libseed supports takes care of these 3 panels here, and the rightmost panel is taken care of by other software packages. This is actually trying to partition the global mesh. Here we are using PET-C to do that. PET-C supports the parallel solution of PDEs. It supports both CPUs and GPUs and the hybrid mode, and it has also support for optimization. And finally, we use Enzyme. Well, I don't think I need to introduce Enzyme here, but what we loved about Enzyme specifically is that it works at the LLVM level, and also it has reverse and forward mode AD in a single toolkit. The focus of our experiments was comparing initial versus current configuration. And if I want to give a brief background here, so if we have a material at the initial state, and if it gets deformed to get here, we have two ways of looking at this deformation or tracking the deformation. One way is to compare it with the initial state with this shape, or in all of those moments looking at the material from the origin of our coordinate system. Sure enough, these two configurations are convertible, and if we push forward means multiplying F and F transpose from left and right, and convert the initial residual to current residual, and doing the same thing with the initial and current Jacobian. So for implementing the initial configuration with enzyme, we previously had the model by analytically taking the derivatives, but for this model we define a strain energy function which returns the the free energy that we saw on the first slide, and then we take the derivative of that function to compute S, or the stress, and this all happens here in the residual evaluation. We would need enzyme additive, the reverse mode, and also we call enzyme augment forward. So we are using the forward split mode here. To compute the stress, it returns the stress and also the tape, the path of the derivative, and that way we can compute the residual. And then, as I mentioned earlier, we can store the data here and then use it in the Jacobian evaluation, and by calling enzyme forward split, we can compute the Jacobian. And you can see the snippet code there as well. So for the current configuration, we tried the forward split mode, but it was a little slow, so we tried just using enzyme additive in the initial, in the residual evaluation, and also in the current configuration, the computing the stress, which is called tau here, is more involved. After taking the derivative, we would need to multiply by this matrix, which is called left Cauchy-Green stress tensor, and then in the Jacobian evaluation, so we didn't store anything here. We just computed tau, and then in the Jacobian evaluation, we had to call enzyme additive again and compute tau because it's needed in the Jacobian, and then we use enzyme forward diff to compute the delta tau which was also needed. So these are the results that we observed. So the analytical current configuration was the fastest, and then the initial AD, and then current AD. So so we can see here, as we increase the number of, the third column is the stored scalar values, and we can see as we increase the number of stored values, it gets slower. However, with current AD, we are just storing 16 scalar values while we have the slowest model. It is about 50% slower than the original current model. So let's see why this is happening. The first row is current analytical, and the second one is current AD, and the green boxes are the residual evaluation functions, and the purple ones are Jacobian functions. So we see in the residual evaluation for computing tau, this is the analytical derivation of the stress. We see the simple expression of stress, while in the current AD we have to take the derivative of psi with respect to E. E is the strain tensor in current configuration, and then multiply it by this matrix. And also in the Jacobian evaluation, in the current analytical, when we are not using AD, we see that delta tau is not needed. So the simplification is such that we don't end up using delta tau, which is really helpful. We would only need to compute. So everything is stored except for delta epsilon that we needed to compute. However, in the current AD evaluation, we had to compute tau twice, take the derivative twice, and then had to compute delta tau here with enzyme. So a lot of simplification was happening with the analytical derivation. So like, yes, AD was very helpful to get the correct result, but it's not as smart as human beings. So we also came up with a wish list for enzymes. So it would be helpful to know in advance the size of the tape and having an enzyme-aware CLANCD to give us an estimate of the size of the tape while developing the code. And also, I would love to compile the code with -0 flag because it would help us to investigate all the variables within a debugging environment in certain contexts. And while we are in that debugging environment, it would help us to call enzyme autodiff in that environment and take the derivatives and see what's going on within that context. And also internal cancellation of tensor operations. So I don't think that enzyme is tensor algebra aware. So if you give me to take the derivative of this function, I would, like A inverse, I would just cancel A inverse and take the derivative of the identity matrix, and it will be a 0 matrix. While if you ask enzyme to take the derivative of A inverse, it will compute A inverse, compute the derivative of A inverse A and some multiplication and addition. So this is what actually was happening with our model, the current model. We were able to use this identity to simplify our model and also some other tensor algebra identities, while enzyme wasn't aware of those simplifications. So that's why current AD was so slow. For the future of our work, we are moving towards modeling plasticity. So far, we have worked with elasticity, which is not a permanent deformation, but in plasticity, well, so if we, for example, stretch a material, we will have a permanent deformation there. So for plasticity, for modeling plasticity, we usually would need to work with 3 scalar functions. We saw free energy on the first slide, and then dissipation potential and the yield surface. These functions usually define how the deformation, like the permanent deformation, can happen in a plastic deformation. So in modeling plasticity, what usually happens is that when material scientists want to take the derivatives and model a plastic material, they spend most of their time taking these derivatives. And most of, if they want to write a paper, most of their papers would be how to deal with these derivatives. But if we were to use an AD tool like enzyme, we would be able just to work with more models or spend, like the material scientists would be able to spend their time on more interesting or challenging tasks, or be more creative, or spend more time on working on validating their models, which is a valuable task in developing new models. Yeah. So that's all I have for today. Thank you.
Thank you. Are there any questions? Comments? Sure.
So one quick question on the tau sort of generation stuff. I'm curious if, so there is a particular activity annotation that Enzyme supports called duplicated no need, where it basically specifies that, in the original forward pass, it will, may need to compute some particular value, but if that's not necessary to compute the reverse pass value, and similar sort of analogs, if it's not needed to be returned for like a forward mode AD as well, it'll be able to avoid recomputing it. I'm wondering, A, if you tried that, and B, if you have tried it and it wasn't sufficient to getting rid of it, if tau isn't really needed for the reverse, why it wasn't able to then be dead code eliminated in that sense.
I don't think. Repeat the question. Okay.
The question
What was
there is a feature in Enzyme called
duplicated no need.
Duplicated no need, and the question is if they tried it and if it did help or didn't.
Yeah, we didn't try that. So, but I'm not familiar with that functionality, so Jed might help.
So I'm not 100% familiar with that feature, but I don't think it's going to help. Basically, the issue is inside of tau, we've got a Jacobian. The derivative of the Jacobian, like gradient of the Jacobian with respect to E, is J times the inverse of this matrix. This 2E minus I inverse. Now, down here, to define tau, we take this gradient and then we multiply by this matrix in parentheses here. So those cancel. There's the inside of the derivative of tau with respect to E, you get this matrix B inverse. And what's in parentheses there is often called B. And so those cancel. But they don't cancel completely, because there were other terms in tau that don't cancel. Those end up getting multiplied by this quantity. And so that's why, like, analytically, you can break out this piece. And analytically, you have an identity here, because that was actually B inverse times this B. And those pieces canceled. And basically, you can push around where you draw the lines in which strain and stress measures you choose to use. But anywhere that you are, you can't get rid of this structural issue. And so really, we want something where we can identify, oh, you've got a matrix inverse, and later outside of that function where the gradient was computed, we have, like, we multiply through and those are supposed to cancel. And I don't know how to abstract that, but it's a really common feature in continuum mechanics.
Yeah, that makes sense. I guess one thing that sort of makes me think about, which this is probably a discussion for the hallway track afterwards, is I wonder if there's something that we could sort of borrow from some of the internal caching algorithms. So as an example, we'll do an analysis on the data flow to figure out what's the minimum set of values that we need to cache, and like try to figure out what can be reevaluated, what's necessary for the derivative. So I kind of wonder if it's potentially possible to extend that mechanism to insert some of this information, and then maybe from that point try to reduce that.
Yeah. Hallway track for sure. Oh, there's a question back there.
Okay. So this question is maybe only directed to the enzyme people in the fun. I'm just I'm just thinking out loud here. Will this get better if enzyme fully shifts to MLIR, where you have those tensor objects, and that could, in theory, cancel at a higher level before enzyme even sees that?
Yeah, I suppose it's a question to Billy.
This is a question for Billy, so.
Sorry, Alex. So I think the answer to that is I think so, but this is something to sort of be tested. So one of the biggest benefits that enzyme has is the fact that it sort of can interoperate with optimizations for wherever those optimizations are. So LVM does have some amount of optimizations, especially if you turn on some of the fancy polyhedral stuff. But clearly, it does not have a specific understanding of a matrix inverse unless you say defined that as matrix inverse like with a custom derivative. Right now, I don't actually think MLAR does have particular operations that would correspond to that simplification, but by virtue of explicitly being the type of thing that you can extend with that feature set, should be able to have those pieces implemented. So I think the answer is, I think it should be, sorry, it's the thing. I see. I think it's fine if the camera doesn't get this part. But so I think the answer is, that should be able to be possible, since as we are indeed, exploring the MLR route for some of these additional pieces. But I think simultaneously, some of the MLR infrastructure for doing those matrix and tensor operations also needs to be done as an optimization, which is not just helpful for AD, but any generic tensor optimization.
Any more questions? We have time for one last question. If not, let's thank the speaker again.